Okay, it's officially 9 o'clock and time to start. So sorry about the mistake in the email I sent out. Test one's chapters 1 through 5, and it's October 9th, the Wednesday. I was sending it to a different class, and it's for Chemistry 100, and that's chapters 1 through 7 is October 1st. So I thought I just copied the link, but I copied the whole message. So you got 2 messages for the price of one. So sorry about that. But you guys have you been getting emails? Oh, you have, okay. Are they helping? Okay. Because I do them to my online students, but I know if weekly, I was like, oh, might as well send the weekly reminders and face-to-face students too. What the heck? All right, so we're in chapter 5 now. Chapter 5, and this is the last chapter for the test, but the kind of all the previous stuff, if you've had chemistry in high school, is probably a review. But those of you who hadn't have chemistry in high school, I know it's new material, and it probably feels like a freight train, especially since we're changing topics so quickly. But that's going to happen through the entire semester, though, unfortunately. We're going to get new mental models pretty much every chapter, sometimes more than one every chapter. So that's just the nature of Chemistry 161. So, okay, so aqueous solutions. Aqueous means in water. And water solutions are very important because, what is it, 60-some%? Is it 2/3 of the Earth is covered in water, thereabouts? So a lot of water here on Earth, and we ourselves are pretty much, I mean, we have protein structure, but we have a lot of water solutions in us as well. So water solutions are very important for industry and life. And we started off talking about concentration. And concentration is the amount per volume. So how much stuff you have in a given volume is your concentration. And chemistry uses a weird one. We use molarity. It's not weird to a chemist, but it's weird colloquially. So as in day-to-day life, you don't think of things in terms of molarity. It's usually parts per mass or parts per volume is when we think of stuff colloquially. So, and let's do this. For instance, so 1 mole of hydrogen chloride, HCl, is 36.45 grams. So if you have 1 mole, 36.45 grams of hydrochloric acid, and you put that into 1 liter of water, you have a 1 mole, or there's 1 mole of hydrochloric acid per liter of solution. So let's do this here. What is the molarity of a solution containing 25.5 grams potassium bromide to make 1.75 liters of solution? So again, I'm trying to get you to think in terms of dimensional analysis. So you're given, what are you given? You're given a mass of potassium bromide. And you're given a volume, 1.75 liters. So 25.5 grams potassium bromide. And then next thing we got to do is look up, well, I don't have to look at it, to figure out the number of moles. So it's moles per, we're looking for, we want to have moles per liter. We're looking for those things. So, and liters is easy. So that's just outright given to us. 1 point, we're going to divide by 1.75 liters. So we got to figure out moles. So moles kBr, and I'll go ahead and I from the previous going around, I don't know if people remember how to do this. So let me go ahead and show you. So here's potassium. Come on, focus, focus. There we go. So we want to figure out, So grams kBr per mole kBr. We look for potassium and look for this number here, and bromine that number there. And there's one of each. So K and Br, so 1 times 39.1 plus 1 times 79.9. So let's see here, that's going to be 80 plus 39, that's 119 grams per mole, right? Am I doing that in my head right? 80 plus 39, yeah, it's 119. So that's the way you do that. You look in the periodic table, you get the bottom numbers, and since it's one of each, you add them together. And we go back to our dimensional analysis. Mole kBr to 119 grams kBr. So notice the grams kBr cancels, and we're left with moles per liter. And so it's just, so use my calculator. What add are you going to give me today, calculator? 25.5, oops, divided by 119, divided by 1.75. And we get 0. Oh, the add today is wish. 122 moles per liter. I'll go ahead and just to give you the complete picture. Quite literally. It's pretty big. Right there, like that. Okay, so now students might be confused. Like before, when I did dimensional analysis, I just went through and canceled all those terms. Why am I just dividing there and don't have anything on the numerator? So again, we're looking for the units. The molarity unit is moles per liter. So I want to get moles per liter. And given information, so what is the molarity? So I'm looking for molarity. So if it's asking for the molarity, I need to have my units be in moles per liter. So I know I need that on the far right of my dimensional analysis. And then what else do I have? I'm giving a mass of potassium bromide and a volume. So, and molarity is moles per liter, so I need to calculate the number of moles divided by the liters. So you can think of it that way, or you can think of it dimensional analysis way to start off with mass and then have the units check out to moles per liter. And I'm getting some feedback from students. They don't know how to do this. So this is the way you figure out the molecular weight of something. You look at the periodic table, you get the numbers, and you add them together times the number of elements atom you have each, and you get the molecular weight, the number of mass and grams per mole of substance. So, questions with this one? Okay, what about diluting solutions? To what volume should you dilute a 0.2 liter of a 15 molar solution to obtain a 3 molar solution? So what it is doesn't really matter. There's a shortcut for this one. You can do dimensional analysis. That's a pain in the butt. An easier one is to use an equation like this. So M1V1 equals M2V2. So M1 is moles per liter times V1 is the liters equals moles per liter. So moles over or times liters. And notice that the liters cancel on both, and we get moles equals moles. So all this equation is saying is the number of moles equals the same number of moles. So Sometimes you might see this solution as C1V1 equals C2V2, C being concentration, or M is molarity. M is molarity, C concentration. You'll see sometimes people write it C instead of M. I mean, whichever one makes you feel better. Philip Williams, the Canadian organic chemist at UH Manoa, he does C1V1 equals C2V2. I don't know if it's a Canadian thing. I don't know what people do in Europe, but we'll see. I know Canada's not in Europe. I'm just saying that there's I don't know what they do in other places. I don't know what they do in China. So to what volume should you dilute? So 0.2 liters of a 15 molar solution to obtain 3 molar. So 3 molar, and our unknown, I'm just use X. I like X as an unknown. So our unknown is the volume, and X equals liters of solution 2. So it's just solve for X, 0.2 times 15 divided by 3. So let's see here, 15 divided by 3 is 5.2 times 5 is 1. So X is 1 liter. So to what volume should you dilute? The answer is 1 liter. Like so. So again, we're talking about volumes. Talking about aqueous solutions and concentration, and how do you do dilutions problems. An easy way to do it is to do this equation, M1V1 equals M2V2, or concentration of 1, volume of 1 equals concentration of 2, volume of 2, substitute concentration for molarity, that one, whatever makes you feel warm and fuzzy. So all this is saying is the number of moles does not change. So if we have 0.2 liters in a 15 molar solution, and we need and we're looking for a 3 molar solution, how much? So if I have a beaker contain this, what volume should I add to reach it to make it 3 liters? I'm sorry, 3 molar. So M1V1 equals M2 volume of 2. We don't know what volume is 2. This is our unknown. So one equation, one unknown, solve the unknown. We get 1 liter. I guess I should be sig fig conscious. Sig fig conscious, it would be 1.00 liters for the 3 sig figs. So everything else is in 3 sig figs. So, questions with this one? All right. 50 milliliters of a half molar solution will make what concentration at 200 milliliters? Man, 15 molar sodium hydroxide, that sounds scary. That would melt gloves. I've worked with 10 molar potassium hydroxide one time, and I spilled some on my hand. I was wearing the nitrile gloves, and I was eating through the nitrile gloves. I looked at that. I remember laughing, like, haha, look at that, and I just ripped off a glove. It's amazing when you see something eat plastic. Another hint of this, as long as you don't necessarily have to use liters, you can use the same units of concentration or volume as long as they're consistent. It doesn't matter. So you can do it as, well, I guess it's M1. you can do it as 0.5 times 50 equals your unknown, 200. Some people think A, eighth molar. How many think B, quarter molar? How many think C, half molar? How many think D, 2 molar? Okay, so we got half a class going for A, eighth molar. Let me come around and see how people are doing. Is anyone getting stuck? Raise your hand if you're stuck. Okay, well, you just came in. I don't know how you could not be stuck.
In the middle of moving, I'm sorry.
No worries. Oh, you got it. It's 50 knots. So your processing side is I don't know what we're getting to 25. Yeah, it's the it's the that's an unknown. Yeah. Yeah. So, I mean, yeah, everyone got it, but you didn't want to play with me. I don't like it when people don't play with me. It makes me a sad panda. So it's 1/8 molar. So a couple mistakes I did see though. When it comes to math, there's something called degrees of freedom. So degrees of freedom, when you want to bind a variable, you have to have the same number of equations as you do variables. So when you have, like if you have one unknown, you need to have one equation. If you have two unknowns, you need two equations, at least independent equations. So you can talk about that more as we get more complex, but when you're solving for an unknown, make sure that you have an equation that has an unknown in it. Otherwise, you'll have an infinite number of solutions. Okay. So, I don't know. Has anyone ever seen the movie Idiocracy? Ah, no, you haven't. Okay. What's that?
Electrolytes is what plants create.
Yeah, Brondo's got electrolytes. Yeah, if you haven't seen the movie, watch it. It'll make you feel better, or maybe worse about the future. I don't know.
Idiocracy.
Yeah.
Okay.
It's not an official homework assignment. I always think of Idiocracy when I see this though, because it's a quote from the movie. Okay. Let's talk about solutions. So what is the definition of a solution? Definition of a solution is a homogeneous mixture. So homogeneous, uniform, a uniform mixture. So most of the time when we think solutions, we think liquids, and specifically aqueous. But there are other types of solutions. So air is a solution. It's a homogeneous mixture of gases. 14 karat gold, 10 karat gold, 18 karat gold, that's a solution. It's a homogeneous mixture. So, and a couple terms. Solvent. Solvent means whatever you have the most of. Solute is the least. So maybe you see someone say, this is solvent free. That means absolutely nothing. It probably means that there's no hydrocarbons in it. So it's probably what they mean. Like, because water is a very common solvent. So ocean water, for instance, it varies by where you're at, but ocean water on average is about 96.5% water and about 3.5% salts. Most dominant salt in ocean water is sodium chloride, but there's other types of salts in ocean salt. Does anybody know what the concentration of salt in cytoplasm and blood plasma is? It's 0.9%. So we humans, if we drink ocean water, our kidneys are not good enough. We get more thirsty by drinking ocean water. So if you're thirsty, don't go and take a refreshing drink from the ocean. That's not going to help you. There are some animals like sea otters. They can drink ocean water and they can actually get refreshed from it. They have very efficient kidneys. But we humans do not. So we're more terrestrial and drink lots of fresh water. With this, what is a solvent? Ocean water, the solvent is water. And the solute are the salts. So solute is the least. Solvent is the most. Solute is the least. The solvent does the dissolving. The solute is the one that's dissolved. And it doesn't matter what phase they are in. I mean, solid, liquid, gas phase. So you can have liquid dissolve a solid, a liquid, and a gas. So you can have water. You can mix it with salt. It dissolves. You can mix it with sugar. It dissolves. You can put a little bit of gases in water. So you can bubble hydrochloric acid. You can put ammonia through water. That dissolves. You can put another liquid in water, like vinegar. Or vinegar is acetic acid. You can put pure acetic acid in water. You can put ethyl alcohol in water. That dissolves. So those are liquids that you can throw together. So, okay, and it's just, the solvent is just by definition whatever you have the most of. I used to list alcoholic beverages, and then my teaching evaluation said I talk about drinking too much. So we will not talk about that. But I do advocate chemistry. Okay, let's talk about types of aqueous solutions. We have strong electrolytes, weak electrolytes, and non-electrolytes. So, and this is usually, aqueous is referred to water. So, water actually is an extremely weak electrolyte, but we consider pure water to be a non-electrolyte. So water, which you will learn in chapter, let's see here, I think it would be 16 or 17 in the book. I haven't gotten that far in this book. It's going to be 16 or 17 in this book. It's water dissociates by 1 times 10 to the minus 7. So any given time, that every 10 millionth water molecule has been broken apart in pure water. That's not very much. And what does electrolyte mean, besides what plants crave? Electrolyte means it conducts electricity. So if you drink sports drinks that have electrolytes in them, they mean salts. So sodium chloride, salt. Water, pure water by itself, does not conduct electricity. Maybe a little tiny bit, but not really. We consider it a non-electrolyte. But if you put salt in water, now that makes water conduct electricity. So to give you an idea, my grandmother, she was swimming in a lake one time, a freshwater lake, a relatively small lake, and when she was there, it got struck by lightning. when she was in the lake, and she told me it felt like she just felt a little bit of buzz, but it didn't but kind of like a big thing, but it didn't. It wasn't any more, maybe a little bit more than like a static electricity charge. And she obviously she survived because I'm here, right? So, so even a lightning bolts have thousands of amps and hundreds of thousands to millions of volts. And a small little lake could not conduct enough electricity to hurt my grandmother when she was a child. So, right. So water. The point of the story is water is not a good conductor. Yeah. Question.
Why do people make it seem like electrolytes and like Gatorade is good if it's just salt, if it just conducts?
Like, well, because salt is a nutrient. When you sweat, you lose salt, and the idea with that, and it depends on where you're at. Like if you ever go, have you ever been to the Grand Canyon? If you go to the Grand Canyon, they have like a sign there that says "Eat salty snacks," and they listed some and they even list an athlete. This athlete completed a marathon, and she died because she went on this hike and she didn't take any salt. So the idea, though, is that if you deplete too much by sweat, if you deplete too much salt, you can die from that and decrease your athletic performance. So humans, we're a weird animal. We're good at some things. We're really good at dissipating heat. So humans are really good at dissipating heat compared to other animals, even better than camels, for instance. So, and we have an incredible endurance. Humans have amazing endurance. We can outrun almost anything. Maybe not a horse or a wolf in a long distance, but we can outrun deer. And there's a couple reasons for that. One thing, we have 2 legs versus 4. Another one is that part of our heat cooling system is we draw our heat by sweat, and we do it right from our blood plasma. But as we do that, we can decrease our salt solution, and that can cause our red blood cells. So let's see, if salt goes down, that would mean then that let me think. Would they swell or would they shrivel? I guess they would. If the salt plasma goes on, that means that water would rush out. It would cause our red blood cells to shrivel. So then we can damage ourselves that way. Okay. Anyways, sorry for the long answer to the short question. So electrolyte means it conducts electricity. A couple types: strong electrolyte, weak electrolyte, non-electrolyte, and water is considered non-electrolyte. So how a strong electrolyte works is it completely breaks apart. So sodium chloride, sodium chloride salt is a strong electrolyte, and if you put salt in water, the salt is dissolved by water, and it just completely breaks apart. And notice now, how does this happen? Sodium chloride is an ionic compound. There's an attraction there. The reason why salt forms a solid is because the positive sodium ions have an attraction to the negative chlorine anions. And water comes along. We haven't learned about polarity yet, but water is a polar molecule, meaning that this end here is negative and this end here is positive. So it's like poles of a magnet, although magnets are magnetism, not electrostatic. So the negative ends surround the sodium ion, and the positive ends surround the chloride ion. And notice that there's 6. Not really shown in the picture. It forms an octahedron. So an octahedron, I can draw a picture of one. It's like a fluorite. This is something I actually can draw. So if you have like a chloride ion, you're going to have the positive end of the water form a octahedron around it. So you have an octahedron forming. And the idea is that the 6 attractions, so there's 6 water molecules with 1 chloride. So the attraction then between these 6 water molecules and the 6 water molecules around, I'm sorry, that's the chloride, the sodium ion. So we have 12 attractions between water molecules versus 1 attraction plus the repulsions of a sodium chloride, I guess sodium and chloride. The idea is that the attractions are greater between the water and then the ionic compound, and then that way it'll dissolve. But since it completely breaks apart and you have charged particles, electricity can travel through these charged particles. And a weak electrolyte, so this is a strong electrolyte. Let me do a non-electrolyte. Non-electrolyte, here's sugar. Sugar is just a molecule, and sugar is just, it doesn't have any charge to it. So if there's no charge, there's no way for electricity to flow. And you'll do a lab with this, looking at electrolytes. A weak electrolyte, this means it partially breaks apart. So what's the difference between a strong electrolyte and a weak electrolyte? Think of it like a couple. So a strong electrolyte is kind of like someone you just met and you shared an Uber ride. So say you're both going to the beach and you took an Uber ride, and as you're going there, you stop by Long's Drugs, and oh, someone jumped in the car, like, hey, nice to meet you. You get to the beach, and what do? You just go your separate ways, right? And a weak electrolyte is kind of like a disgusting couple in love. So what happens when a disgusting couple in love goes to the beach? They're hanging out together all the time. All the time. You see them all the time. And suddenly one of them has to go to the bathroom. So what do? They go to the bathroom, they break apart, and the other person's sitting there, in the bathroom. Come out. Oh, it took you forever. Come here, So that's a weak electrolyte. A weak electrolyte likes to be bound together, but every once in a while, they break apart. They go to the bathroom, they take a shower, they go to class. A weak electrolyte, if the other partner would be sitting in the window, hey, when you come out of class, so I can hold your hand. So that's that, and by a molecule is a stable group of atoms, so when an ion separates, it'll come right back as soon as it can. So that's a weak electrolyte. And what are weak electrolytes? Weak acids and weak bases. I know we haven't talked about those yet, but vinegar is a weak acid, acetic acid is a weak acid, which means it stays mostly bound. But every once in a while, about 1 or 2% of the vinegar, the acetic acid molecules, depending on the concentration, breaks apart. And then that small amount of breaking apart means it will slightly conduct electricity. So, and this is what you can see here. So here is a non-electrolyte, and there is no current going through. And like I said, you'll do this in lab. A weak electrolyte, there is a little bit of a light in the light bulb, and a strong electrolyte, there's a very bright light. So here is vinegar, and you can see vinegar and water. It's mostly together. It's shown here to be only about a quarter broken apart, but it's much less than that. So so these are acetic acid molecules right there, and then this one right here is broken apart. So, but it really doesn't break apart 25% of the time. It's more like 1 or 2%. It's very, very strongly bound. And here's sodium chloride. Here's your Uber ride to the beach. All right, we got here. See you later. I'll never see you again in my life. Bye. Breaks apart. Okay. Questions on this? All right. So which solution conducts electricity? So in one corner we have potassium bromide. The other corner we have glucose, C6H12O6. And then we have methanol. So which one conducts electricity? Well, this is an ionic compound, and ionic compounds, and it is also soluble, which we'll talk about solubility next. This one breaks apart completely, therefore the potassium bromide is what's soluble. I'm sorry, these are all soluble. It will break apart, and since it's a positive and negative ion, it does conduct electricity. So glucose is a molecule. How can you look at this and determine it's all a molecule? They're all nonmetals. So it's all nonmetals. Same thing with C, methanol. It's all nonmetals. So they don't break apart. The exception to this, of course, would be something like ammonium chloride, NH4Cl. That is all nonmetals, but this is also a polyatomic. This is ammonium is a polyatomic ion, and you'll be given a chart with a polyatomic ion, but I don't think I'm going to ask you that question. So, but this is considered ionic bond. But the general rule of thumb is, though, that a group of nonmetals is going to be a non-electrolyte or a weak electrolyte. So we're not going to go too far into this because we're going to cover acids and bases much more in depth in next semester. Okay. Questions? All right, another thing you do not have to memorize but have to know how to do. So we're going to move on and talk about solubility. So, and these are the types of questions from what I hear. I've never taken the MCAT, but apparently they love to ask these questions on the MCAT because it's logic. This is all logic and it's reading charts. So these compounds are generally soluble. So lithium, sodium, potassium, and ammonium. So exceptions to this? None. No exceptions. I mean soluble in water. So nitrate and acetate, always soluble in water, no exceptions. And chloride, bromide, iodide, these tend to be soluble, but we have these exceptions. Silver, mercury, and lead. So chloride, bromide, iodide are soluble with the exceptions of silver, mercury, and lead. Okay, and sulfate tends to be soluble with the exception of strontium, barium, lead, silver, and calcium. So alkaline earths and silver, basically. So these are soluble. Now these tend to be insoluble. Hydroxide and sulfide are soluble with the exceptions of lithium, sodium, potassium, ammonium, because ammonium, these are always soluble. And sulfide is soluble with the alkaline earths, calcium, strontium, barium. And hydroxide is slightly soluble with calcium, strontium, or barium. And I don't know if I really agree with this, but maybe with barium. Calcium hydroxide you can drink. So you can even take it with an upset stomach, and it's lime water. It's alkaline water. All these silly stuff you see in. But and it won't hurt you. You don't want to rub it, at the same time, you don't want to rub it in your eyes. That would hurt if you put it in your eyes. So that's why I tell you not to put your fingerprints in cement, because that can burn, especially if you take it and rub your eyes after you like carve your initials in cement, because that could hurt your eyes if you rub your eyes with it. It's calcium hydroxide is wet cement. Okay, carbonate and phosphate, CO3 minus 2, PO4 minus 3. These are soluble if it's alkali or ammonium, no other exceptions. So you're looking at this, what's the general trend? The general trend is, notice the ones that are soluble are the ones that are +1, -1. Those are the ones that are soluble. And if you have these bigger charges, so carbonate -2, phosphate -3, these big charges, these tend to be insoluble. Insoluble means it won't dissolve. So, and the reason why these big charges won't dissolve is because, remember, water has to come in and then surround the ion. And the idea is that the 6 waters, sometimes it's 4 waters, depending on what's being dissolved. It can form a tetrahedron or octahedron typically. So 4 waters or 6 waters that surround it. The attraction between those 4 and those 6 waters and the other ion, the attraction there is greater than the attraction between the straight cation and anion. And if you start having bigger charges, the attraction is greater. Therefore, it won't dissolve. So if you're wondering why it works this way, it works this way. But you will have to know how to use these charts, a chart like this. Hopefully I've explained the logic. So let's do some problems. So let's say if these compounds are soluble or insoluble. Let me just write them up here. It might be easier. PbCl2, CuCl2, calcium nitrate, and barium sulfate. Oh, it's just there's no. Okay. So we have to determine if these are soluble or insoluble. So start with lead chloride. So lead chloride here. Chlorides tend to be soluble, but lead plus 2 is an exception. So because of this, this one is not soluble. I'm going to put I for insoluble or not soluble. So you see that lead chloride, so I'm looking at chlorides. Chlorides tend to be soluble, but lead is an exception to show that this is insoluble. Then do the same idea, changing colors here, to copper chloride. Chlorides, again, tend to be soluble. Copper is not an exception. Copper is not silver, mercury, or lead. Therefore, this is soluble. Are you following my logic? Okay, calcium nitrate. So calcium nitrate, remember these parentheses mean that there's 2 of those NO3s. Not that it really matters for this one, but for calcium nitrate, nitrates are all soluble, no exceptions. This is definitely soluble. So all nitrates are soluble. Barium sulfate. So barium sulfate here. Sulfate tends to be soluble, but barium is an exception. So this one here is insoluble. And if you've ever taken a CT scan and had to take the barium sulfate contrast agent, I can tell you this stuff tastes terrible. Yeah, a couple of you will agree. They lied to me. That orange flavored barium sulfate still tastes terrible. There is no going around how terrible this stuff tastes. But, okay. But is definitely insoluble. So, questions with how to do this? Okay. Now, next thing I talk about are precipitation reactions. So, precipitation reaction. So, say you have potassium iodide and lead nitrate. These are both soluble, and if you mix them together in a solution, you get this lead iodide precipitate. It's this yellow stuff that falls to the bottom of a beaker. You're going to do a precipitation lab as well to figure out solubility rules. At least as long as no one's changed the schedule on me. We'll see. But, meaning you take 2 beakers and you pour one into the other, and then if stuff falls down, that's known as a precipitate. And remember, we talked about that with the alkaline earths. The reason why it's called alkaline earths because the metals, they're alkaline, they're bases if you put them in water, but then if you mix them together with this stuff, they form precipitates. So it's like they're alkaline, but they have solid dirt in them. So dirt is in one of the earth, wind, fire, water. So they're alkaline earths. So that's why we call them alkaline earths, because they're insoluble. They form insoluble compounds. So insoluble compounds, and then these sink to the bottom of the solution. Well, typically they precipitate down to the bottom because they tend to be more dense than water. You can get stuff that floats on the top too. Those are called the supplicants. But there's many more precipitates than there are supplicants, at least mixing in organic solids. Okay, so that's precipitation. It goes down. And another thing for my teacher evaluations, please forgive the heteronormality of this. I know that there's other combinations possible, but this is easy to describe, so colloquially. So if you want to figure out if there is a precipitate going to happen, think of a cation, kind of like a male, and an anion like a female, and I could flip them back and forth. I don't know. Either way you want to put it, but this is just an easy way to describe it. And the idea is, so cations are not attracted to other cations. Cations are only attracted to anions, and anions are only attracted to cations. Two anions are not attracted to each other. So if you have, like, if you have something like potassium iodide and lead nitrate, I should do plus and minus. I'll go ahead and put another nitrate. So we have potassium iodide and lead nitrate. They can do a partner exchange reaction. This is actually called a partner exchange reaction. So, and the question is, when in a solution, it's not just standing there. A solution, things are moving around and they're bumping into each other. And the question is, and these are soluble, so when you throw potassium iodide into water, it dissolves, it breaks apart. You throw lead nitrate in the water, it dissolves, breaks apart. But it's moving around solution. And eventually, the potassium ion is going to bump into a nitrate, and a lead's going to bump into an iodide. So the question is, when they bump into each other, is one of them going to turn out to be insoluble and have a greater attraction for each other than the solution? If one of these is insoluble, then yes, a precipitate will form. If these are both soluble, then nothing's going to happen, no reaction. Okay, so let's do example for this. So potassium carbonate and nickel chloride. So if this mixes, and these are both soluble, so let's look up here the chart. So potassium's right here. Potassium is an alkali. All alkalis are soluble, and carbonates tend to be insoluble. Then it's nickel chloride. Chlorides tend to be soluble. Nickel is not an exception, therefore nickel chloride is soluble. So these are both soluble. And what is this going to form? This is going to form KCl plus NiCO3. And how am I doing some of this? The charge. So if you look at the charge, potassium is +1, and you can look at a chart, or you can, by the fact that potassium is +1, carbonate is -2. Chloride is -1 because it's an alkali. All alkalis, or not alkali, I'm sorry, halogen. Jeez. Halogens are -1, which means nickel is +2. And if you want to balance this, it would be 2 KCl then on this, and then nickel carbonate. Now the question is potassium chloride soluble, is nickel carbonate soluble? So let's go back to the chart. So we're looking at KCl and nickel carbonate. So potassium, alkali metal, always soluble. This one is soluble. Nickel carbonate, so carbonate is down here. Carbonates are insoluble with the exception of alkalis and ammonium. Therefore, nickel carbonate, this is insoluble. So this one goes down. This one goes down in solution. So this one actually does form a solid. So how do you write this equation? How would you write this? Let me move this over. You would say this is aqueous. So you'd write the whole thing as K2CO3 aqueous plus nickel Cl2 aqueous yields 2 KCl aqueous plus nickel CO3 solid. In old textbooks, they sometimes, instead of saying a solid, they use a down arrow. So if you ever see an old textbook that has a down arrow, that means precipitate. And some foreign countries do that still, like Vietnam. I had a Vietnamese student and says, yes, we do that in chemistry in Vietnam, we put a down arrow. And there's also up arrows. Can anyone guess what an up arrow is?
Soluble.
What?
Soluble.
Soluble? No, it's not soluble. Good guess,
The
though.
down one was insoluble.
Supplicant.
Not supplicant. Good guess, too. Gas. You mix stuff together, can form gases. All good guesses. Okay. Now, let's look at this reaction here. So sodium nitrate and lithium sulfate. This is going to form lithium nitrate and sodium sulfate. And let's put a 2 here and a 2 here. So that's balanced. So the question is lithium nitrate soluble and is sodium sulfate soluble? And remember, all alkalis are soluble, all nitrates are soluble. So lithium nitrate is definitely soluble, it's aqueous. Sodium sulfate, all sodium ions are soluble. This one is also soluble. So this is one of those examples where absolutely nothing happens. And what do you do when you see something like this? You write no reaction. And RXN, that is chemistry shorthand for reaction. So if you see someone say no RXN, that means absolutely nothing happens. You're expecting something to fall out. You're expecting something to blow up. You're getting excited. You mix it together, and then absolutely nothing happens. That is our no reaction. So questions of this. Hopefully my analogy still holds with the pardon the heteronormality, and hope no one gets offended. But it seems to be, I found it as easiest to explain it that way. Question? For where? Okay. So balancing chemical equation. I just wanted to balance it. So let me ignore the numbers. I'll erase the numbers. So balancing the charges, sodium is +1, nitrate is -1, lithium is +1, sulfate is -2. So since this is +1, that forces it to be -2. Or you can look in the charts, and it'll say that for sulfate is a -2 polyatomic ion. So partner exchange, lithium is going to bond with nitrate here, lithium nitrate. Sulfate's going to bond with sodium, and since sodium is +1, we need 2 sodiums for the sulfate -2. Okay, and now let's balance it. So I'll start with lithiums, 2 lithiums here, so which means we need 2 lithiums here. So it's going to be a 1-to-2 ratio here. If there are 2 nitrates, let me write 2 here. You can, when you balance, you can do it by atom or you can do it by groups. Or if you want to do it by nitrogen, that's fine too. But nitrate groups or nitrogen atom, there's 2 of them here, which means you need 2 of them here. So you need a 2 there. And now let's look at the last one for sulfate. 1 sulfur here, 1 sulfate here, 1 sulfate here. And so that way, this is fine. So if you want to go through and count each atom, though, so let's double check on all the atoms. 2 sodiums, 2 sodiums. 2 lithiums, 2 lithiums. 1 nitrogen, 1 nitrogen, 1 sulfur, 1 sulfur. 3 times 2 is 6, plus 4 is 10, 10 oxygens. 2 times 3 is 6, plus 4 is 10, 10 oxygens there. So I was just balancing it quickly. Questions? Okay. So we put copper chloride and lead nitrate. Are we going to make anything? Maybe I'll just copy this. Erase all this. Can I make it smaller? I guess not. So I'm putting copper chloride, CuCl2, and lead nitrate. Is anything going to react? So how many think we're going to have form solid copper nitrate? How many think we're going to form solid lead chloride? How many think we're making dichloride nitrate? How many think there's no reaction? So these are two anions. C is two anions. This is wrong. So it's not. So it's not C. We need a cation and an anion. So it's either A, B, or D. And you're going to mix these, and it's going to be copper nitrate and lead chloride, lead 2 chloride. Question is either of these insoluble? So let me come around. Okay, I'll start this side.
Do you understand that if you have copper chloride and they mix, that the possible compounds are copper nitrate and chloride? it'll come up. So it's like I don't drink beer super Friday. So if you're mistaken, I don't drink beer unless it's Friday. Today Friday, no, I'm not drinking beer. It's Friday, I'm drinking beer. Yes. Friday's my beer drinking day. Saturday, no, not Saturday. Just Friday. So. So because of that, this tends to be song with that exception on the third and fourth. So because Friday is not so. Things don't like so you're not gonna have. And you remember that. It's 20 or 3 times in the 23rd. So like, let's say that water was +1, and that means you would have same charges. That was yeah. Soluble means it's all. There's a point. Just solve it. Makes you solutions to this. What's some of the solve? Are you allowed? Yeah, you're gonna do a lab like this for users. And you're gonna look to see if I mean, this will. I mean, you should get a logic to it. You also know that. I mean, let's do. You should know. So lead is plus 2 or plus 4. You don't have to. But you have to let's say you would have to know this. Yeah. Yeah. You don't know. We'll think about it and sleep on it and dream about chemistry. Yes, this is considered this week. This should be a perceptual trauma. There's some that's just constant. Some that magnitude of knowledge or
We were following along. We came to the same conclusion.
Okay, it makes sense.
Yeah.
Good. Oh, okay. That's the cat eye answer. Yeah, positive. Do you think positive, positive? You got it. That's good. So, this one right here. So, do you understand soluble? Taking this tends to be soluble. So sulfate is soluble, except for sulfate is soluble unless it's very disgusting. So it's like I don't eat chocolate unless it's Thursday. So rule is I don't eat chocolate unless it's maybe you say it on. I eat chocolate unless it's Thursday. So today's Wednesday. Do I eat chocolate? Yes. Because I eat chocolate except for Thursday. Tomorrow's Thursday. Do I eat chocolate? Because I can eat chocolate, but it's Thursday. I don't eat chocolate. That's the idea of that. So this tends to be soluble, except for yeah. Yeah. So the answer would be what do you confuse okay. Yeah. Yeah. So this is like saying I drink water every day. So right, I drink water every day. I eat breakfast every day. So I'm eating lunch. On Tuesdays and Wednesdays I eat lunch. So Monday I eat lunch. Tuesday I'll eat lunch. Generally this is true. It's true. And then you just apply the logic. So copper nitrate is always like chloride. So chloride tends to be soluble. That exception.
get that this is a solid. I got there by reading this and figuring that out. My question is, okay, so the down arrow means solid? What does the
Yeah, it
down
means,
arrow mean?
it means, it's better to say solid, yeah. I'm just.
So down means solid and up means gas.
Yeah, but that's the old one. Yeah.
Books and paper, yes. And then, so what happened to the copper nitrate at the top?
It stays in solution.
But you crossed it out. So
It means it's not, it
not
doesn't react.
reactive, like nothing.
Yes.
It just stays in the solution
Yeah.
and it just chills out.
It's
as
copper,
nothing happens.
copper and nitrate blissfully
Okay.
floats around in water.
Okay. I mean, then yes,
Yeah.
I got that.
Yeah.
That actually makes sense
Yeah.
to me.
Because what I mean, remember we talked about physical and chemical changes? Forming copper chloride, I'm sorry, lead chloride, this is a chemical change. You form a new compound that doesn't dissolve in water.
Mm-hmm.
So I partially cross it out because it's a physical change. It's not even a physical change, there's no change. Copper and nitrate were floating in water, dissolved, and after you mix it, it's still floating in water, dissolved. Nothing happens.
Okay. So when they ask you, tell if something reacts, the only way you can tell is by doing this formula. That's the only way you can tell. Or
I mean,
somebody
you could-
like you can tell by looking at it.
But I
With
mean,
your eyes
I'm also,
closed.
yeah, but I mean, I've been studying chemistry for a while. You can tell chemical reactions, you can tell they happen by a few ways. There's a few indicators for them. One is the formation of a new compound.
Mhm.
In this case, you form a new compound that doesn't dissolve in water.
Okay.
So that's a telltale sign. Chemical reactions sometimes produce light and heat.
Mhm.
So that doesn't, but you can form light and heat without a chemical reaction.
Mhm.
But sometimes, that is an indication that a chemical reaction might happen.
Mhm.
And let's see here. Also, electric discharge. Similarly, sometimes electricity happens.
Okay.
So I mean, they're just.
I know it's like the questions sometimes are odd. Does it tell if there's a reaction? How do I tell? I don't know. So,
Yeah, I mean, in this case, if you and you're in the lab, or you're in Peter Fisher's lab.
Yes, I was in
Yeah.
yesterday. It
Yeah.
was great.
Good.
It was actually
Better
great.
than the last one.
Much.
Yeah. So I mean, you're going to be doing an experiment on precipitation, and you're going to mix things together, and they'll look cloudy, and you're going to use drops and look cloudy.
Mhm.
If you see the cloudy stuff, that means that you form a new compound, because the other compounds can dissolve in water, and now you have a new compound that doesn't dissolve in water.
Mhm.
The fact that you observe that there's something that doesn't dissolve in water indicates that a new compound was formed, which indicates that there was a chemical reaction.
Okay.
Right. So that's
That's
one.
why this only includes the one compound, but it's insoluble as opposed to no reaction because a compound happened, so there
Yeah.
was some reaction.
Yeah. So something happened.
Yeah. Okay. Thank you.
Yeah.
Yay! I got something right. If I call a newspaper.
No, you got lots of things right. You took this class, for instance. That's right. Okay, so remember though, don't kill the messenger. Chemistry is an observational science. I'm just reporting what we've observed. Right? Any complaints have to go to someone else, not me. So, but my shut up alarm is probably less than a minute away. I guess my iPad's got a different time than my cell phone. I have a shut up alarm. Okay, but it looks like class is over then. We'll see you guys then on Monday of next week. Yep, there's my shut up alarm.